I'm going to be reporting on progress in an extremely old endeavor in physics, which is the theory of scattering. So I think everyone here is at some level familiar with this. Scattering is like the first topic we would cover in classical mechanics. Maybe a bit later in quantum physics, you would study things like quantum transition amplitudes, which encode the probabilities for particles to interact through scattering. Okay, those objects are called quantum scattering amplitudes, and that's the topic of my talk today. Now, as you can imagine, these scattering amplitudes are kind of incredibly important for actually comparing theories to experiment. In the end of the day, we have to map our high-minded ideas and concepts to actual observables that someone can measure, and that requires computing probabilities or scattering amplitudes. But what is perhaps less well appreciated is that scattering amplitudes actually are beautifully intricate objects mathematically that are worthy of study in and of themselves. Okay. Indeed, I will try to argue today that by looking at them, we can actually learn about structures residing within theories we've been studying for decades, and in some cases, as long as a century, which include general relativity, the strong interactions, and various parts of the Standard Model. Okay? So I will talk about how particles like gravitons, gluons, pions, things that we normally do not think of as being kind of stated in the same sentence are actually connected at the hip in an extremely direct way, a very direct way. They're all connected and in some sense equivalent in a way that I'll show you. So on the one side, by studying these amplitudes, literally the observables themselves, we can learn about structure that I should emphasize is not at all explained from the point of view of symmetries. Okay? There's no Lagrangian, Hamiltonian, or equations of motion picture for why these structures exist, and yet we know they are there. That's the kind of first part of my talk. The second part of my talk is about using those ideas, those discovered structures, to kind of leverage calculations and understanding outside of particle physics. So these ideas all originated in the context of collider physics. They were developed over many decades to understand the data that came out of things like the Large Hadron Collider. But I will talk about almost purposely very disparate topics in physics, which are not related to particle physics, like fluid dynamics and the dynamics of black holes, precisely to emphasize that these ideas are very general. Okay? The basic principle, basic principles I'll outline, apply broadly. I'll really kind of touch on the case of fluid dynamics and the application of these ideas to the Navier-Stokes equations. And then the final part of my talk will be about kind of work starting around 2019, where we use these ideas from scattering amplitudes that ultimately came from collider physics, map them all the way to a very physical problem relevant to experiments, which is the binary in-spiral problem that is important for gravitational wave observatories. Okay. In particular, I'll tell you how we can use and have used these methods to compute what is now the state-of-the-art calculations for the Hamiltonian for two black holes in binary in-spiral in Einstein's general relativity, in what's called the post-Minkowskian expansion, and how those tools are now the tools to use, okay? So that's an interesting story that has lineage all the way from kind of high-minded particle physics and string theory ideas all the way down to like celestial mechanics. Okay. This is a colloquium, so I'm gonna start zoomed out. And I wanted to tell you my own personal motivation for why I'm interested in amplitudes. In our conferences, we have very different folks from all walks of life, like, of course, particle physicists and string theorists and collider physicists. But more recently, we've had folks from other fields, like pure mathematics, cosmology, even gravitational wave physics, all with different motivations. Despite the fact that the physics is different, there's some overarching connectivity between these ideas. And to me, if I had to distill in just a sentence, like, what is the game here? What are we asking? It has to do with a super basic question, which is what defines a theory? Okay. So if you ask someone this in a physics department, they'll tell you, oh, I know what defines a theory. The equations of motion define it, or the Lagrangian or the Hamiltonian. I just write down an equation, and that's what the theory is. Okay. And that's a fine answer, but let's unpack that slightly. Consider this for particle mechanics. So in particle mechanics, I would write down an action, which is an integral over some Lagrangian, and I would have, some, let's say, harmonic oscillator type Lagrangian. But secretly, these are just repackaging physical principles, okay? In particular, when we write down, it's hard to see here, but this is locality and time. When we write down a Lagrangian that is integrated over one time and only one time, that is an assumption. We've assumed that there isn't a bilocal Lagrangian with multiple times in play. There's a single time. This means that the interactions are local in time. That's just an assumption that we built in. Okay, you can't undo the assumption, it's built in. Furthermore, we have, again, this is also hard to see, we have other assumptions like parity symmetry, for instance, the fact that the potential is has a symmetry under mirror reflection. Those are the principles. Everything not fixed by principles is something you measure, okay? So for instance, the spring constant or the mass, those by definition can take on many different values. They are thus not fixed by an overarching principle, which is why we have to ask an experimentalist to measure them. Okay? So by this viewpoint, when people talk about the 19 parameters of the standard model, they're talking about the 19 parameters in the standard model that are not fixed by principles. That's why they have to be measured, and they're not predictions from some overarching principle. Okay, so things that people measure are not fixed by principles. The same basic idea holds when we kind of uplift to the grown-up version of how we think about physics, which is something called quantum field theory, which is the merger of quantum mechanics and special relativity. It's basically the same game. We have an action which is integrated locally over space and time, so it's local in space-time. We have some set of assumptions like Lorentz symmetry or whatever symmetries we have in our theory, and some set of particles and so on and so forth. But in the end of the day, everything we don't fix, it has to be measured. Okay, things like masses, coupling constants, and so on. Okay, good. Now, if I had to kind of, okay, I've kind of belabored the point, but the basic thing I'm getting at is that Lagrangians and Hamiltonians and so on are not the starting point. They're an intermediary between a set of physics principles and some observable that we compute, like a scattering amplitude or correlation function or free energy or what have you. Okay. Now, if I had to say what is the purpose of our program, it's essentially to completely skip this middle step and go directly from physics principles to observables. Okay, so this is sometimes called the modern scattering amplitudes program, but it basically means the following. Don't start with a Lagrangian. Don't start with a Hamiltonian. Throw out everything you know from the textbook. Instead, write down a function space for your set of observables. Okay, what I like quite explicitly mean is write down an ansatz function, which depends on your kinematic observable, kinematic variables, like your momenta or your polarizations and energy. Whatever your thing depends on, write a function for it. If that function has no constraints and is completely free, you'll get nowhere. You need to assume things. You need to assume the same things you would have assumed normally. But with those assumptions, you can constrain this ansatz and sculpt out the actual physical answer, which agrees with the kind of conventional picture. Okay. Now this, again, may seem like vague, but like at a very precise level, you can build these functions, sculpt out solutions based on those physical principles and determine the space of theories that are consistent, or I should say the space of amplitudes that are consistent with your physical principles. Okay. A very nice thing about this, which I'll touch on again in a bit, is that this allows you to rule out theories in a much more abstract way. So for instance, if someone said, can you write down a theory that has 1, 2, 3, 4, 5 sets of principles manifested? Well, you could say, well, I'm not clever enough. I can't find the Lagrangian, but maybe it exists. But I won't answer that question because maybe I don't know how to write down the Lagrangian. But this type of procedure lets you actually solve that problem. You assume the principles, build a function, and if no such function can exhibit all those principles, then you've ruled out any theory, any putative theory that has those principles. Okay, so you can find that principles are mutually inconsistent this way without knowing what the Lagrangian is, which is part of the power. Now, you could ask reasonably, why should I bother doing it in this very difficult way? After all, you know, Lagrangians, Hamiltonians are great. That's the first thing we ever learn. Well, it turns out that at a very technical level, using Lagrangians in quantum field theory generates a big headache, which is connected with something called Feynman diagrams. So again, I'm not assuming everyone here is a particle physicist or has this background, but you've probably seen at some point in your lives maybe diagrams like this. I saw this in the theory wing floor, diagrams that look kind of mysterious like this. These are called Feynman diagrams. Here's my 30-second crash course on Feynman diagrams. So this is the picture actually of Richard Feynman. This is like a framed picture in our Feynman lecture hall with him in Caltech regalia and holding this staff. Okay? And you can see embedded in his staff is a diagram. Okay? And this is a so-called Feynman diagram. A Feynman diagram does two things at the same time. The first thing it does is it tells you the process you're asking about. So this is a process which is two electron, positron come in, they merge into a photon, which then disintegrates into a pair of muons. Okay, so there's just some particles in the standard model. So it does the one thing, which is tell you what you're talking about. But it's also an equation. Okay, so professionals who study this realize that each diagrammatic part of this figure actually is a mathematical function. Okay, of the momenta and the polarizations and the things that this process depends on. So in particular, this line and these vertices all stand for factors, literal mathematical factors that you multiply out, and that resulting expression is the scattering amplitude. Okay, so what you do is you sum over all possible diagrams like this, you add up all of them, and you just get a function, and that thing squared is the probability for this event to occur. Okay, so that's what a Feynman diagram is in a minute. Okay, now this is at no point am I saying that Feynman diagrams are not working or incorrect. They are incredibly powerful. Famously, using them and other tools from quantum field theory, we have some of the most precise predictions, arguably in all of science. One of the flagship such predictions is G-2 of the electron, which between theory and experiment is an incredible agreement at many decimal points. Okay, this is made possible precisely by this kind of these kinds of techniques. So there's nothing wrong with it. It's correct. Okay, the thing that's not great about it is it's really complicated to use. Okay, so Feynman diagrams beyond the very simplest processes are immensely complicated. Let me tell you what I mean by that in an example. Okay, so hopefully you know that the proton is not fundamental. It has stuff inside it. That stuff is quarks and gluons. Okay, if you don't know what quarks and gluons are, that's fine. I'm just going to tell you what you need to know about the gluon, which at least for the next 30 minutes is relatively simple. A gluon is a lot like a photon in the sense that it is a massless particle that has spin 1, and it has two polarizations. Okay, just like the photon has like a left polarization and a right polarization, which we'll sometimes call plus and minus, the gluon also has two polarizations. Okay, that's essentially all you're going to need to know for the next few minutes. Okay, when we talk about scattering at the Large Hadron Collider, we of course scatter protons, but there are such high energies that basically the stuff inside the proton is scattering, so we can talk about gluon scattering. So that's about gluon scattering. 2 gluons come in, 3 gluons come out. This is kind of a lower order process. You can see this matters for the LHC. This would be proton-proton to 3 jets. Okay, this is something that actually we care about. And if you computed this using the standard methods, you can't see this very well, you would get this giant 200-term expression. Okay, so if you just use the textbook, you open up your favorite quantum field theory textbook and just use the rules that we teach students, this is the answer. It is 200 terms. Each term is a complicated function of momenta, polarizations, and so on. Okay, and that's just it. You're done. That's the nature is ugly, and that's the way the world is. Okay. Now, of course, the story is more interesting because the true answer is much, much simpler. Oh, you're gonna maybe we could turn the lights off so you can see you want to see the slides probably. I'm guessing. Yeah. I like to see the slides too. Oh, perfect. That's great. Thank you so much. Yeah. Yeah. Okay, great. Now you can see, yeah, if you couldn't see this blob, you wouldn't realize that this is very painful to compute. This is actually the expression. Okay, but the answer is secretly much simpler, as you can imagine. In particular, let's say I chose all the polarizations to be right circularly polarized. Okay, I'm being a little sloppy with inverse out, but let me not elide that. Let me elide that. But I pick some set of polarizations, and I make sure the energy and momentum is conserved. You'll learn that that very complicated 200-term expression is just 0. Okay, that was just a really bad way to write 0. That literally is just 0. In fact, this amplitude vanishes for all configurations of right and left circular polarizations, except for one, this is called the so-called Park-Taylor formula, and it's non-zero and written in terms of some variables that we're going to see throughout this talk, which are called spin or helicity variables, these angle brackets. Sometimes you'll see square brackets too, angle brackets and square brackets. You don't need to know what they are. All you need to know is that there isn't buried immense complexity inside these things. These are not like convoluted generalized hypergeometric functions. These are just literal rewritings of P1, P2, P3, P4, P5, the momenta. Okay, so just by reshuffling the way we talk about momenta, those 200 terms compactify into a single term. Okay, and this was well known ever since the work of Park and Taylor, who computed these amplitudes originally. Of course, the way they computed it was pages and pages of algebra, and then they found that it's simplified. Okay. Now, of course, as physicists, when we see this as your final answer, and we see the preceding intermediate steps are insanely complicated, we should immediately think there should be a better way to compute. Okay? There should be some theory that spits this out immediately as the most direct output of the formalism. Okay? And indeed, there's many different programs, including like the so-called celestial holography program and the twistor theory program, which are all based on the fact that this object has many interpretations that relate to conformal field theory and all kinds of high-minded structures. Okay, but the basic point is that this is beautiful. This object, you can see structure in it already just by eye, and using that you can glean and kind of roll back and figure out what that structure is. Okay. Now, this is not just a property of gluons, which famously is a very nice theory. It's part of the standard model. It's also very nice. It's also true for gravitons. Okay? Now, what do I mean by gravitons? So when I talk about graviton scattering, this is all I mean. I mean, take Einstein's general relativity and think of a background of multiple gravitational waves. Okay? This is not a physical process that we're going to see anytime soon in an experiment, but with the theory we can compute the kind of evolution of those scattering gravitational waves order by order in Newton's constant. Okay, so there's nonlinearities. At lowest order, they just pass through each other, but eventually they start interacting. Feynman and DeWitt wrote down the Feynman diagrams for that process a long time ago. Basically, these are the functions associated with the vertices and the lines in those Feynman diagrams I showed before. They're a giant mess. Each of these is, multiple many terms. If you computed the amplitude with standard Feynman diagrams, you get roughly 100 kilobytes worth of just terms. I couldn't even show it on the screen. But as you can imagine, in the right variables again, it compactifies to one term. It is one single term again. This is all the content of 2-to-2 graviton scattering. The two gravitational waves come in, two come out. This is the only combination that is actually non-zero. Okay, so again, it's immensely simpler. Okay. Now, everything I've said here really should seem like the statement of compression. I'm telling you that the way we compute is massively redundant. The final answer is far simpler. So I can't help but plug a recent paper that we wrote applying recent tools in machine learning to this question. Okay, this is just a one-off. I just thought I'd mention it, which is that, well, we have this mechanistic procedure where we would like to simplify some huge expression to as simplest possible expression we can. It's perfectly framed for the target of machine learning. In this paper, we basically retrofitted a transformer neural network that was open sourced by Facebook Meta to just simplify expressions of this type. We even put it online, so you can even plug in your own expressions to do it. Okay, it's quite compelling, at least when I was using it. You input some giant equation, you basically let it crank. I could tell you the details, but let me not get into it here. And in the end, it will spit out precisely these formulas that I mentioned. Okay, so it gives like an invariant notion of what is the simplest possible version of an amplitude that can exist. It will give you the top 10 nicest versions of it. And there is an intrinsic sense in which these nice formulas are truly simpler. Okay. One of the more gratifying parts of this project was after we realized it could spit out these formulas, I started giving it really complicated scattering amplitudes with like 5 gravitons and many scalars and gravitons. And it was spitting out formulas I've never seen before, which we then published. So it's my first paper where equations, which no human derived, but are clearly interesting, are there and came entirely from a machine instead. Okay, this is something I could touch on, but let me move on. Now, I've told you that the kind of standard way we compute is very complex, overly complex. It's natural to ask, why is that? And the irony is that it's complex because of something we normally celebrate in physics, which is something called gauge symmetry. Okay, now you're used to this from, let's say, electrodynamics. The kind of simplest version of this is the fact that the voltage is not well defined globally. It's some constant, which doesn't matter. Maybe a bit later, you learn about a much bigger version of that so-called symmetry, which is called gauge symmetry, where you can shift the electric potential and the vector potential in this way. Where the important caveat is the electromagnetic fields themselves, the things that you actually probe, are invariant. Okay. Now, in the modern picture, we understand that this is, it's a very powerful tool, gauge symmetry, but it's actually entirely a property of humans' representation of the physics, which is not necessary. We know this because whenever you compute, the first thing you do is gauge fix. You pick a voltage. How cherished can a principle be if the first thing you do is break the symmetry to do a calculation? And in fact, after you compute, if your answer depended on the gauge, you know you were wrong. Okay? So secretly, it's a gauge symmetry is a nice tool, but it better disappear from everything that's physical. And that's because it's a trick for, rather famously, this is the way that high energy theorists think about this. It's a way of manifesting two properties at the same time. two properties that are true, that are exhibited in nature, namely Lorentz invariance and locality. Okay, the two things I kind of started with at the beginning of this talk, but we want them at the same time. So in order to have Lorentz invariance, we have to introduce some degree of freedom with as a 4 vector, so it's Lorentz invariant. But 4 is too many degrees of freedom. There's only 2 polarizations of the photon, so we introduce gauge symmetries to reduce those degrees of freedom. That's the basic picture. Okay? But that induces a huge amount of redundancy. Okay? It just means that every time you wrote something down, you had to remove a bunch of stuff that you added, essentially for formalism's sake. Now, the byproduct of this is a massive explosion in just complexity in calculations. So if you just computed with Feynman diagrams, gluon scattering at 4, 5, 6, 7, 8 numbers of external particles, it swiftly grows. There's 34,000 different diagrams, each of which has many terms in it. While with modern methods, which I'll talk about in the remainder of this colloquium, it's much simpler. Okay, these 1, 1, 3, 6, and 20 are kind of cousins to that very simple monomial expression I wrote before. Okay, there's way more direct methods to get at these amplitudes. Okay, now you might think from my discussion that this is some general annoyance about theories with gauge symmetry or theories with diffeomorphism invariance like gravity. Okay, these are famously theories that have this redundancy that we're familiar with. So if you thought only about, let's say, phonons in materials, or you only cared about the inflaton and early universal cosmology, or the Higgs boson, you might say, okay, scalar field. That's got to be scalar field, got no spin, beautifully simple. What you see is what you get, surely. That's also not true. Okay, so even the simplest theory you could ever think of, which is a scalar field theory, actually has a redundancy that we rarely discuss. Okay, let me show it to you. This is maybe more technical for those who kind of are more well versed with quantum field theory. But if I wrote down an interacting scalar field theory of this form, okay, this is just a depiction of a scalar phi. That is to say, a particle with no spin, with many interactions and self-interactions, which have absolutely no special coupling. So lambda 1, lambda 2, these coupling constants are totally arbitrary. Okay. Now, if someone gave you this toy universe and said, compute the 2 to 2 scattering, the 2 to 3 scattering, compute the scattering amplitudes, you'd find that they are all 0. Every one of them is 0. Okay. In fact, the way they'd be 0 would be very frustrating. You'd have to compute every single Feynman diagram. You'd have to make sure you keep track of all the energies, do it exactly right. And only when you add everything will you get 0. Okay, it's always 0. Okay. Now, if you didn't know more about quantum field theory, you would say, oh, that's weird. There must be something magic about this, even though lambda 1 and lambda 2 are arbitrary and so on. But it turns out it's obvious once you know a little bit more about quantum field theory, which is the following. I can map this Lagrangian by sending phi to some other function of phi to another Lagrangian, which has no interactions. Okay? I can, in other words, choose G here to eliminate this whole train of couplings to just leave me with a theory which has absolutely nothing here other than free propagation. Okay. Now, this is not a symmetry transformation. I'm not doing what we would normally do, which is perform some transformation, make sure the Lagrangian is invariant. In fact, the Lagrangian is not invariant. It changed. It went from this to that. But as a maybe less known fact is that under such changes of variables, the scattering amplitudes are unchanged. These physical observables are unchanged. Okay? It may seem exotic here, but you're used to this from classical mechanics. In classical mechanics, you can compute something with a Lagrangian in Cartesian coordinates, okay? And you get an answer for some scattering angle or binding energy or what have you. Now you do a transformation that doesn't leave the Lagrangian the same. You go to polar coordinates, okay? Cartesian to polar is not an invariance of the action. It changes the action, okay? But nevertheless, you can now compute in those coordinates. And if you compute scattering angle, binding energy, something physical, it's the same. Okay? It doesn't matter the coordinates you compute with. That is precisely the same for quantum field theory. What it means is there's a huge redundancy in the way we even describe physics, which is that whenever anyone writes a Lagrangian, there's actually secretly an infinite train of other Lagrangians that are exactly the same physically. So in other words, take your favorite Lagrangian and do a change of variables and get a second Lagrangian, which looks different, but has the same physics. Now, let's say you wanted to find structure inside a theory, but you didn't know what the symmetries were. How would you find it? Well, you could just keep hopping down, keep finding other field bases, keep changing variables until you kind of land on polar coordinates. And then you just discovered, cylindrical symmetry. You could try that, but that's a very inefficient way to find structure, to just keep hunting. A much better way is to just jump directly to the amplitude. Literally compute something which does not care about what your variables are at all, and then study that answer, okay? And that's precisely why these amplitudes are much simpler than the Lagrangians or any of the preceding kind of paraphernalia we use to actually compute with, okay? And that's what I want to tell you about now, which is by studying this amplitude directly, we can actually learn something new. And I'm going to talk about 3 senses in which that's true, okay? So these are the remainder of my talk. Okay, I'm first going to tell you about why, by looking at amplitudes directly, we can see that the laws of nature are very rigid. Okay? I'm sure many of you, like me, probably had the same experience in high school, which was when you learned about the 1/r² force law. We're like, oh, that's amazing. It's in gravity. It's also in electrodynamics. And usually the words folks would say is, well, it's 1/r² because it's like a beautiful formula and like physics is beautiful and that's the way it is. Okay, that's not a great answer, actually. It doesn't explain why it couldn't have been 1/r, not to the 2, but to the 2.0076. Why is it not something different? Turns out that there's a very explicit sense, which I'll show you, where those other variations are literally just excluded. They are excluded by physical principles, which means something more interesting has happened. It's not just that the laws of physics are beautiful, it's that they literally couldn't be different. If they were any different, they would be inconsistent. Okay? And that is a rigidity of these theories, which you can argue for only once you've kind of let go of the Lagrangian, let go of that usual picture for how we think about theories. So that's the first thing I'll tell you about. It'll be kind of reinventing the wheel in some sense, because we'll encounter things we know, but it's, I think, a powerful picture. The second thing I want to tell you about is how a lot of the theories aspects of the Standard Model, these are all parts of the Standard Model in some sense, are actually secretly connected, and that you can see this connection by studying the amplitudes. Okay, so especially like gravitons and pions, these are things you almost like never see together in a sentence in a physics talk, but I will tell you how they are all kind of the same. Okay, and maybe I'll just say it just to spoil the punchline. The basic point is that if someone handed you all the scattering amplitudes in gravity, they just gave them to you. An oracle goes to you and just gives you all of them at 4, 5, 6, 7 point. Sitting inside all of them is all the amplitudes for gluons, pions, and a whole gambit of other theories, just sitting inside them that you can sculpt out in a very mechanistic way, which I'll show you. Okay, so there is this hidden unity, which is by no means obvious if you have studied these theories otherwise. And then in the last maybe 10 minutes, I'll talk about, maybe 15 minutes maybe, I'll talk about how we can take those structures, ideas, and methodology and apply them way outside the bounds of particle physics to fluid mechanics, and then I'll finish with a discussion of our results for LIGO. Okay, good. So let me now continue and just talk about the rigidity of laws of nature. So here's the basic idea. We're not assuming a Lagrangian, we're not assuming a Hamiltonian, we're just going to assume principles, like special relativity, and something I'll call locality, which I'll make a little more clear in a second. Now, we're very much used to thinking of gravity, and the theory of gravitons, Einstein's general relativity, as an example of a theory that has a massless spin 2 particle, which is the graviton, which is self-interacting. Okay. But what I want to show you right now is that the implication goes the other direction. If I just tell you, write down a consistent theory of a self-interacting massless spin 2 particle, there is only one answer. There is no other answer than general relativity up to corrections that we'll make precise. Okay, so what do I precisely mean by that? Well, I have to introduce the most important ingredient in any of this scattering amplitude stuff, which luckily is also the most famous equation in all of physics, equals mc², which you probably know is just a series expansion of a much bigger expansion, which is a relationship between energy and momentum. Okay, energy and momentum for physical particles are not independent. The energy is dictated by the momentum. I'll sometimes call this the on-shell condition. And it's a property that particles, when they're evolving on their own, just have to satisfy. It's the most kind of intrinsic feature of scattering amplitudes. When you don't assume this, you're not talking about a physical process. Okay, so in some sense, all that complexity I was mentioning before, those ugly formulas, they all stem from not assuming this properly. Okay, so this is very important. Now, we can now show you briskly kind of a version of how this bootstrap principle works. Let's think about three-particle scattering. Okay, I kind of already told you about propagation, which is relativistic. Let's talk about three particles interacting through some vertex, but without knowing what a Lagrangian is. Well, the idea for this is that we simply write down some function of P1, P2, and P3, any function, and we demand that it's Lorentz invariant. Okay. So it turns out for massless three-point amplitudes, and actually also for massive ones, this entirely fixes what this function can be. I'm not going to go through the algebra of why this is true, but it forces the amplitude to either be something of the form of products of those angle brackets we saw before or products of those square brackets. And again, the insides of this don't matter. The point is it's really simple, and there's no other function it can be other than this. Okay, that's fixed by Lorentz invariance. Now, if we apply that idea to a particle with spin 1, like the gluon, or a particle with spin 2 with the graviton, like the graviton, it turns out that we just get a unique three-point amplitude. Okay, so this is the three-particle scattering amplitude for a minus, minus, plus polarized gluon, the same thing for the graviton, and these are just the expressions. We bootstrap them because there's literally no other function that has Lorentz invariant properties. If you decided to do this the hard way, you like busted out your quantum field theory textbook, computed a Feynman diagram, evaluated it, you would just get these expressions through much more difficult means. This is the direct shortcut. Okay. Let me already point out something interesting about these formulas, which you'll probably notice, which is that if I take the gluon amplitudes and I just square them, I literally take the functions and square them, you get the graviton amplitudes, okay? Now, if you've ever studied gravity or the strong interactions, that should be very confusing why that would be true. The Feynman diagrams, all the mechanics looks different. The underlying physics is different, but the square of gluons equals graviton. Okay, that's the first observation of a general fact, which actually applies at any number of point scattering, which I'm going to call gluon squared equals graviton, which is also sometimes called the double copy, which is the statement that two copies of gluons, that is to say the square of gluons, is equal to graviton. We'll return to that with a vengeance a bit later. Okay, now, but the overarching point here is that we know the three-particle amplitudes with no worry. It's fixed by Lorentz invariance. Now, of course, scattering is much more interesting because we have 4-point, 5-point, and higher point, arbitrarily high point. Here we have another ingredient, which I call locality. It's just a fancy word of saying something that's very intuitive, okay, which is the following. Let's say I gave you some putative 4-point amplitude, which is like two particles in, two particles out. There's a consistency condition that it has to satisfy, which is basically like a resonance condition. Okay. In particular, if I take P1 and P2 and I tune their momenta such that the sum of the momenta squares to 0. That's another way of saying the intermediate particle satisfies the equation of motion. Then I should get a singularity. This is just like if you like tune a laser on resonance. Okay, you're like going on resonance. There should be a pole. You should hit something. Something should blow up. That pole is a divergent 1/0 factor, but physically it corresponds to a feature where if you tune these momenta appropriately, this 2-to-2 process disintegrates into two separate processes. The first process is 1 and 2 coming together and forming a third particle. That third particle then travels locally in space-time at great distance, which gives you an infinity, that pole here, and then it disintegrates and decays. Okay? So it's just a kinematic regime where there's two separate processes. We know the separate process amplitudes. It's the three-point amplitude we just computed. Okay? So this gives you a constraint from higher point to lower point, which lets you bootstrap higher point. Okay, so concretely, what we do is we write down an ansatz, literally an ansatz function for the 4-point amplitude, and we just demand that it satisfies this constraint. Okay. And what you will do is slowly reconstruct all the theories of nature that you're familiar with. So if you did this with gluons, you build up Yang-Mills. If you do this for gravitons, you build up general relativity. Okay, so you can build up order by order all the G-Newton corrections of general relativity. This is a construction that has no elevators, equivalence principle, all that is missing. So that physical nuance is gone. But it tells you that the underlying essence is nothing more than two facts, special relativity here and locality. Okay. Good. So with this procedure, you can now sculpt out the space of allowed theories that could ever possibly exist. You can build a map of theory space without having a Lagrangian for any point. Okay. What do I mean by that? Well, let's do the following. Build an ansatz. Literally build a function ansatz, which has, for which you assume some spin. So you constrain it so it describes spin 1, spin 2, or spin 3 particles. And then also demand that it has some coupling constant, dimensionality of the coupling constant, which is controlled by something called rho. Okay, basically it's fixing the dimensionality of your interactions, and then just try to ask, can I build functions that have these properties, that describe this spin and have this dimensionality of the coupling constant? And you will find that there is allowed and forbidden regions. Okay, in particular, a massless spin 3 particle with self interactions is ruled out. Okay, that doesn't exist. Okay, that's a well-known QFT result for completely different arguments, but this is a first, a different type of bottom-up construction for why that is. More notably, the particles that show up in the standard model actually live right in the boundary of existence. So this is general relativity. This is the strong interactions. This is phi cube theory, which arguably is in the standard model through the Higgs trilinear coupling. But the point is, for whatever reason, the standard model lives on the edge. Okay. The reason you could see why that had to be is actually not that surprising. As I told you, every free parameter, every measurable parameter in a theory represents something not fixed by principles. If you look at GR, it's got G Newton as its coupling constant, just G Newton. There aren't two, there's not three, there's just G Newton. For the strong interactions, there's alpha strong, okay, the strong coupling constant. There's not another one. If you imposed more constraints, you'd have to fix those coupling constants, okay? So it'd be over-constrained, okay? So the fact that we have a lot of single parameter theories is why these are on the edge of existence. Of course, there's other theories that are not on the edge of existence, at least in this plot, like the theory of pions, phi-4 theory, so-called higher dimension operators. Those are less constrained, and they're less nice in that kind of invariant sense, okay? And these can also show up as corrections to the standard model. That's totally allowed. So there's no free lunch here, okay? Good. Now, this kind of idea of constructing all numbers of particles of scattering with factorization and with Lorentz invariance has been generalized in many different directions, including massive particles, loops, diverse dimensions, okay? Much of that work had been about gauge theories and gravity, maybe some scalar field theories, but there's a whole class of theories that particle physicists like myself and like Matt very much like to study, which are called effective field theories, which are viewed as kind of a more practical tool. What are they? Well, they're practical, they're powerful, they're everywhere, but they also have limited validity, okay? So the idea is an effective field theory is something where you calculate, but you know that if you calculate outside of a certain regime, it will give you nonsense. So you have to stay within bounds. And it's a great way of simplifying the dynamics. So famously, it was invented for a theory of superconductivity, also for the physics of the strong interactions, but it's been generalized in many different ways, including to inflation, large-scale structure, fluid dynamics, dark matter. There's tons of EFTs. Let me tell you the basic idea of an EFT with the classical mechanics model. Okay, so here we have, imagine you have a potential for a ball at the kind of bottom of a wine bottle here. Okay, it's a two-dimensional particle in the sense that it can move in the kind of radial direction and on the angular direction. Okay, this is just a particle, literally a particle in this potential. But at low energies, it settles to the basin. Okay, so at high energies, it has 2 degrees of freedom, an angle and a radial variable. But at low energies, it just settles onto this basin, which is a one-dimensional problem, just on a circle. Okay, so the way we'd say this is there's an effective field theory for this setup, which is just a one-dimensional particle in a circle. Okay, that's at low energies, that's how it behaves. Now, crucially, there's properties of the full theory that are still encoded at low energies. In particular, because this wine bottle is cylindrically symmetric, that is precisely why this basin is a circle. Okay? That circle encodes the original cylindrical symmetry of the system. So effective field theories know about symmetries, at least in nice cases like this. Okay. Now, I said the word symmetry, and when I say symmetry, I need coordinates, and I told you I'm throwing out coordinates. We're doing this coordinate-free, Lagrangian-free. So how can I possibly recapture the physics of a symmetry if I don't have fields or particles, Lagrangians, or equations of motion? Well, it turns out that there's a proxy to those features. Okay? Even if I don't have an action and I don't have notions of symmetry, it turns out that the infrared behavior of scattering encodes all this physics. Okay? By infrared behavior, I just mean very low wavelength properties of scattering amplitude. The way to see that is you can kind of see this here also. If I just took this ball at the bottom of the basin and I just gave it a very tiny kick, so it was very slowly moving around the basin, it probes that whole basin, right? In some sense, that low frequency mode knows about that big circle. Okay, so it has a sense of that symmetry. So that's why low frequency oscillations have some connectivity to the symmetry properties. At a technical level, don't worry about this slide. It's just some fact that if we fix a property of the infrared limit of amplitudes, that is to say, we take the momentum of an external leg to zero, we demand some behavior. This turns out to be precisely a proxy to that symmetry statement. Okay, so there's the correspondence between those. The details don't matter, but it lets us draw a map, again, of space, of theory space, where we have the coupling constant here, and here we have instead some parameter sigma, which is a characteristic of those infrared properties, that low frequency property I mentioned. And again, we can rule in and rule out. Like before, we find that part of the standard model lives on this diagram. The theory of pions, also known as the chiral Lagrangian nonlinear sigma model, like literally particles in the standard model, lives right here for some reason. These two other theories are not part of the standard model as far as we can tell, but they show up all over the place in theory circles because of cosmology. So they're hypothetical models of, say, inflation or of modified gravity that has been discussed at length for completely different reasons. And for some reason, they just show up also in this plot. Okay, they're also connected. Okay. So yeah, it's part of the standard model, not part of the standard model. Okay, and of course, there's a bulk, which is less constrained. Okay, now, so I've hopefully made the point that lots of theories or aspects of the standard model that we have observed and know are true live on the edge of existence. These kind of special edge theories. But I now want to tell you a more remarkable fact, which is that not only are these theories on the edge, but every theory I've mentioned on the edge is connected to another one. Okay, they're all linked together in a very direct way. Okay, we already saw one version of that from gluon squared equals graviton. Okay, but it turns out that that's true also for pions and gravitons and Galileans and all those other funny names I mentioned. Okay, and that's what I want to tell you about next, which is this hidden connectivity. To do that, I have to kind of backtrack slightly because I was a little simplifying when I talked about gluons. I told you there were like photons and they are, that's true, but they have another really crucial property, which is that there's multiple of them. Okay, so you've maybe heard this term colors of the gluon. All that is, color of a gluon is literally just a species label. So there's multiple gluons, like literally an index which labels what they are. So there's not just momentum, there's also a color label, which in the standard model runs from 1 to 8. Okay, and it's just like literally 8 types of photon, if you like. Okay, but we call the whole thing a gluon together. Okay? We've ignored it entirely, okay? But it's like, if you like, just an index that labels them. It seems innocuous, but something interesting can be observed. We've only focused on the momentum dependence. I talked about momenta and polarizations. That's, of course, interesting. But there's also this so-called structure constant, which basically tells you which color gluon couples to which other color gluon. Just like an interaction string, okay? But it tells you who couples to what, okay? This is called the structure constant of the gauge theory. Okay. Now, when you look at this, you can already see kind of a parity here. Okay, these are showing up together. Is there a reason for that? Okay, this is kinematics, namely momenta. This is color. Could color and kinematics be related or interchangeable? Okay, they seem to show up together. Okay, this should sound very exotic. Kinematics is momenta. Color is like a label, like a literal index. Turns out, not only are they related, they're actually dual and equivalent in a very precise way. So let's take this for the case of the gluon. Okay? If I take a gluon, that gluon scattering amplitude I mentioned before, you can expand it and it will depend on momenta and it will depend on color. Okay? And again, color is just a proxy for the interactions, the interaction strengths between gluons. If you look at these C's, CS, CT, and CU are just color factors. They're products of these F's I showed you before. These are just numbers, like literally numbers, like actual numbers that you multiply out. And it's just a fact, something called the Jacobi identity that these sum to 0. Okay, it's a fact about math. Okay, the coupling constants happen to sum to 0 in this funny way. Now, there's also the kinematics, which I've called NS, NT, and NU. That's where the momenta, the polarizations, all the stuff that tells you about energies and so on live. And then something here remarkable happens, which is that the kinematics satisfies the same identity, the same so-called Jacobi identity. Okay, even though this has nothing to do with, facts about mathematics, It just turns out that if you plug in the kinematics for external momenta and polarizations that are physical and on shell, this is still true. Okay. This is called the kinematic Jacobi identity. It suggests, implies that momenta somehow have some kind of underlying structure which parallels color. Now you can go one level further and make the following leap. Let's say color and kinematics are somehow the same or dual. I can literally take color and kinematics and swap them. Let's do that. So let's take all the color labels, CS, CT, and CU, and just replace them with another copy of NS, NT, and NU. Okay, so what do we get? We get some new function that has no color. Okay, so if I said this is an amplitude, it would be for colorless theory. There'd be no species label, so it's one single type of particle. And on top of that, it would have more momenta because I squared these ends and the number of momenta doubled. Turns out this is not just some random function. This is the 4-point graviton scattering. Okay, so this is essentially a crazy shortcut for computing gravitational observables. Okay, so the most efficient way to compute something in gravity is to not compute it in gravity at all, but to instead compute it in Yang-Mills and then square it. Okay, so this is the most efficient way to compute, especially since there's decades of work basically dedicated to computing the top thing efficiently, gluon scatter. It's a total art form, not even art form. It's mechanistic. It's the opposite of an art form. It's like completely systematized and understood. That is a much faster way to compute any observable in gravity in perturbation theory in this way. This fact, I'll just say, is true for any number of particles. So the 50 graviton amplitude, which would be impossible to compute with standard means, you can get trivially from taking the 20 gluon amplitude, which is easy to compute, and then squaring it in this way. Okay, so this is a proven fact about gravity and gluons. So I'm going to show this kind of schematically in the following way, that gluon amplitude squared equals graviton, and just accept that I'm telling you that this can be done at endpoint and included even in higher loop. Okay, if we want to go beyond the Born approximation. Okay, now, so this already is a kind of incredible fact. It goes a little bit further. So the number of double copies is actually very great. So you don't have to just think about gluons and gravitons. It turns out that this double copy also applies to pions. Okay, pions are a much different degree of freedom than any of these other particles that show up in the standard model. They don't have color, but they have a different species index called flavor. Okay? But if you treat this so-called flavor index as if it were color and use the exact same rules with no changes, identical workflow, you get another set of amplitudes, which were the other edge cases I mentioned before. Okay? You can do even crazier things like take a gluon amplitude and a pion amplitude and put them together, and you get amplitudes in Born-Infeld theory, which in 1930 was conceived of as a nonlinear completion of electrodynamics. Okay, so these all have shown up in previous incarnations, but they're all related by this square relation. So kind of miraculously, if you have a theory you like that has a single parameter and that has some nice property, it's a very decent chance it's on one side of an equation like this. There's a whole table of these, like 3 pages of tables like this that have equal signs and squaring relation. Okay. Now, why is the double copy true? So this would be the topic of a whole nother seminar that I could give, which would be more technical. But one way of thinking about it has to do with this statement I made earlier, which is that the graviton S matrix actually contains every other S matrix that I've described. Okay. Explicitly, I'm saying that if someone handed you the S matrix, the scattering amplitudes for all numbers of gravitons scattering, you can sculpt out from it every other scattering amplitude, okay, which is already a highly non-trivial statement. Okay, this is how pions can descend from gravitons. I want to emphasize that the kind of unity that you're seeing here has nothing to do with grand unified theory. So you might sometimes hear about grand unified theories or string theory. This is not that type of unification, because this up-down direction is not energy. This is spin. And this left-right direction is just derivatives in the number of interactions. So this is not your kind of standard way of unifying things. Okay? But again, to be hyper-concrete, just a bunch of formulas, those operations are literally differential operators. So what I'm saying is if you take the graviton amplitude and write it in terms of polarizations and momenta, and you just take derivatives with these objects, which I won't prove here, you will just get all the other amplitude. Okay, so it's easy as pie. This is actually how I personally would compute anything, which is to first start with gluons, square them to get gravitons, and then get everything else, okay, at any number of particles, which is why our papers have formulas for any numbers of particle scattering in every one of these theories. Okay, this is now considered basically a solved problem. Okay, now this property that you can kind of go from gravity to other theories just by differential operators, this at least has some maybe explanatory power because it tells you that any property of gravity is a property of one of its descendants. You can see that by taking a property and then applying a differential operator to it. So one such property is the double copy I mentioned. And if you apply those differential operators, you precisely get the other double copies. So all these square relations descend from some mother square relation, which is the graviton and the gluon. There's other like real physicsy phenomena that are also mapped onto each other. So if you take Newton's laws or Coulomb's laws, at least in their incarnation in what are called soft theorems, which are also related to memory effects, it turns out that under these mappings, they all map onto each other. So Newton's law maps to Coulomb's law, maps to the so-called infrared zeros of the pion. So these are all also connected directly by this mapping. Okay? So this is the sense in which these theories are not at all just friends, but actually deeply connected in a way that quite explicit. Okay, in my final minutes here, let me now change gears slightly and show you how those structures, which I still find kind of rather wondrous and miraculous, can just be practically used for other types of physics, okay? Just the basic idea of bootstrapping something from first principles, the basic idea of exploiting hidden structure. We can apply this well beyond gravity or pions or gluons. Let me first mention the case of fluid dynamics, okay? I'll go through this maybe a little fast. You could ask about the scattering of stuff, like solids and fluids. Famously, the Navier-Stokes equation has a very nice kind of, structural similarity to Maxwell theory. We know this because the transverse condition for the photon field is very similar to a solenoidal condition you get from an incompressible fluid. So there's already this kind of like just at the level of math, some kind of like similarity. Also, the Navier-Stokes equation itself is like Yang-Mills or QCD in the sense that it's nominally a very simple equation, but has emergent nonlinearities, which certainly in the turbulent regime are incredibly complicated. Okay, so it's a very complicated system in principle, but dictated by this simple equation. Okay. Now, it's been known for more than 50 years that you can write down scattering amplitudes for fluid dynamics. This was done by Wild in 1961. And the idea is very simple. If you just solve the Navier-Stokes equations for a fluid velocity, u of x, in the presence of some source j, you get a tree-like structure. Just what happens when you solve equations of motion. And we can just interpret this kind of object as a scattering amplitude. It's a tree, it has many legs, there's an interaction, and you can perturbatively compute the velocity field in this way. Okay. It was not very useful for folks interested in the turbulent problem because it precisely works in the regime where you have high viscosity, where you're very close to the heat equation in your dynamics. But nevertheless, this is a perturbation theory for fluid dynamics that you can study. There's even Feynman diagrams and so on and so forth. Okay. Again, I'm not going to show you the details, but the upshot is that the things I've mentioned, using locality and the relationship between higher point to lower point to get the full scattering set of scattering amplitudes, infrared structure, which in this case comes from the breaking of Lorentz symmetry in condensed matter systems, and even the double copy, they all appear. They all appear in Navier-Stokes, and it allows you to compute those velocity fields in a different way. Okay? Not necessarily one that would actually help you solve turbulence by any means, but in an interesting recasting of some of those, some of that formula. Okay, again, this is telegraphic, but I just wanted to mention that this actually can be done. There's also a double copy for fluids, which is also kind of interesting. Okay, now in the last part of my talk here, I think my last few minutes, I want to mention again, yet a different application of these ideas, but one which is very, very experimentally relevant, I would say, which is the question of the binary black hole in spiral problem. Okay. And this is based on work that we started at Caltech, starting all the way back from the end of 2018. But we were very excited by these ideas because I've already told you, the most efficient way to compute perturbatively in gravity is to not, and to compute in another theory, and then use that as a cheat code to get to the answer. So there's a very natural question of whether we could say something about gravitational wave physics. And indeed, if you know anything about gravitational wave physics, there's kind of three regimes where a merger happens. In the in-spiral regime, the two black holes are kind of far from each other, kind of weakly coupled. That is a place where perturbation theory can be used. When they merge, it's strong field, and you need numerical relativity. And then afterwards, in ring down, you might use perturbation theory again, using Kerr perturbation theory. But this initial in-spiral phase is a place where we kind of use general relativity in the weak field regime, which is the kind of language we need to use our tools. So we immediately jumped on this, which was the in-spiral dynamics. There was an existing way to think about the physics, which was called post-Newtonian, okay? Which is simply the statement that you want to compute the dynamics between two black holes in a particular expansion where the velocities are small and the black holes are far from each other. Okay, so they're far from each other relative to their sizes, and they're slow. Okay, and you work in this order by order in order to compute corrections from Einstein's general relativity to Newton's law. Okay? This was the kind of classical way to do it. This is a program that existed for 100 years. Yeah. There's another way to compute, which is now called the post-Minkowskian approximation, which is to not expand in velocity, to keep all orders in velocity, but expand only in g. Okay. In particle physics, we just call this perturbation theory, because we would never expand in v squared in a relativistic theory. We would keep it, because all those v squared corrections are related by relativity. Okay. So it's in some sense much more natural just to do each order in g and get every power in v squared for free. That is the kind of essence of what our work was. So before we decided to start thinking about this, this is a kind of a map of what was calculated and known. Okay, these are calculations that get fed directly into the waveforms and the chirp that they compare data to. So there's a very complicated sausage making machine where they combine numerical relativity, ring down, and these perturbative calculations to get a prediction. And this was what was known previously. These have, this is 0 PN is just Newton. 1 PN was Einstein, Infeld, and Hoffman after the conception of general relativity. And then 74, 2000, 2014, this was the kind of state of the art. Okay, just going order by order. I'm not going to tell you about our detailed calculation, but hopefully it's clear that if you're solving Einstein's equations, you're going to have lots of diagrams spiritually of the same type that I showed for gluons. There's a lot of redundancy because you're using a Lagrangian. Okay, here's a sample set of diagrams computed kind of in the kind of standard methods. There's nothing wrong with it, but it just gets hard and complicated to do. Okay, the point of our work was to basically use the double copy and QCD to jump to the head of the line and compute it way more simply. And I'll just show you the final product of the work, which was these new post-Minkowskian results. So this is really just to show that we're responsible. We literally computed the Hamiltonian for two black holes. We extracted that directly from the scattering amplitudes for black holes, which were obtained from Yang-Mills amplitudes. So we had many steps, but this expression essentially repackages an infinite number of terms in the velocity expansion. So the first few terms, okay, I'll write it this way. So this was our first paper, and this was our second paper. You can see that the point of this is that we kind of compute at any given order in G, and we get infinity number of terms going to the right. Okay, which is a win from before, which was always finite. Okay, so when these papers came out, folks slowly checked v to the 10th and v to the 12th and so on, v to the 6th and v to the 8th. So that's a slow check, but we have the entire answer, and we very swiftly had results that couldn't be compared to known results. At this point, this whole program has its own legs. This has now gone to 4 p.m. There's now results as of last couple of months ago that are at 5 p.m. Yeah, you can kind of slowly see that things are slowly eating away at this, chipping away at this big plane. Our work is still complementary to post-Newtonian because there's still this triangle here. There's still work in both directions. But I think the more gratifying thing is that the tools I've mentioned from scattering amplitudes in many cases are being kind of absorbed by the existing folks who compute this. The folks who are kind of doing this even with standard methods are starting to see the power of these methods and actually are starting to use them, which I think is maybe the most important outgrowth. Now, our very first citation from this paper we were very excited by was from the LIGO the LIGO group at Potsdam who actually make the waveforms. So these are the folks that like build the model that feeds in all the theory data to compare against experiment. Of course, they knew Decidus because they literally asked us to compute this. So there's no coincidence. They knew of our methods and they asked us to compute this to a higher order. I won't get into details of this, but the point is higher order calculations are more precise. Whether that makes a difference for an actual observation is a whole set of other questions, which I don't think we're there yet to make a real difference just because of precision. But my take is we're going to be doing gravitational wave physics forever. So at some point, precision will matter. Much like at LHC, at some point, computing at some loop order wave seemed crazy, but eventually it became crucial to actually compare against the theories we have. So this is our first citation, and then I'll finish with the second citation we got, which I was very excited about, which was this formula in the foreground of this Big Bang Theory episode, which actually came out and is our result before our published paper. So this is actually the first place the result happened, and actually has a typo, so I wouldn't use that. Yeah. So there's a factor of 2 wrong. Yeah. Anyway, let me wrap up here. Hopefully I've been able to convince you or convey to you that there's a lot of exciting things in scattering amplitudes if you just stare at them as objects that should be studied. But they all have the same flavor, which is some magic thing happened, and we have no real clue why the miracle happened. Okay, as I said, there's not a symmetry statement or a Lagrangian statement for many of these structures. I think it's personally much of my ongoing work is about trying to demystify this from like more pedestrian, symmetry type arguments. But there's tons of structure that we just don't understand, and we're using it to compute new things. But hopefully, at some point, we'll actually be able to explain them in a way that doesn't even need amplitudes, the crutch, to derive it. And hopefully I can report on that at some point in the future. Thank you for your time, and let me stop there.